multi-dimensional scaling is amazing. If you want to work with high-dimensional data and lower the dimension to something humans can work with, or find patterns using graphs like this or this, then multidimensional scaling can be very useful. What is multidimensional scaling, or MDS for short? Well, it's basically an algorithm that takes in a table of distances and turns it into a map, which preserves those distances. While finding this map, it will also find the variables it thinks are important to the plot, which can help with reducing the dimensionality of the data. Depending on how you use it, it can be more of an approximation of a map. The map gives you a sense of the data. Kind of like how when you close your eyes, you have a sense of where things in the room are. I'll explain. For example, let's think about your room. There might be stuff in your room, like a table, a door, or a window, which, for now, we can describe in 2D space, like a set of XY coordinates. Now, let's say one day I reorganize some stuff in your room, measure the distances between each of those things, and give you this data set of how far things are from each other in your room. Could you know what your room looks like before even entering it, just using that set of distances? Now, I know what you're thinking. Let's go and start at one point and draw some circles around it to try to find a visualization. But I would ask you, how do you know whether you should draw a circle or a sphere? Because I didn't tell you whether the distances I found were measured in 2D or 3D. How am I even measuring the distance? Well, in 2D, I would probably be using a string that's stuck to the floor, going from object to object. And in 3D, you could probably imagine me using that string from, say, the top of your door to the edge of your table. However, on an axis using vectors, we can calculate this using the Euclidean distance. In 2D, it's basically using Pythagoras' theorem on the x and y components of a point. I'm hoping you've seen that before. In 3D, it's similar. We just square the components of the vectors and add them up. Also, you may notice you can get this formula from just dot producting the vector by itself. So that's just a starter on Euclidean distance. But the question still remains. How would you know whether you have to go out of the page or not? Let's take a deeper look into the Euclidean distance. How do we actually convert our coordinates to Euclidean distances? Well, we can think of our coordinates as vectors. And when we use the formula, what we're basically doing is traveling along the reverse of one vector and up the other one. So in this case, we're going from A1 to the origin to A2, and that gives us the direction vector from A1 to A2, whose norm we can calculate. Usually when you calculate the norm, you'll square root it, but for our purposes, we'll just keep it squared. And then we just repeat that process for each of the points. Let's take a closer look at this formula. What we're doing is just subtracting a vector from another and then summing the squares of that. If we expand the quadratic in the summation, we get something that noticeably looks like a dot product. So our distances are expressible as inner products or dot products. Therefore, a relevant matrix here is constructed, known as the inner product matrix, whose entries correspond to the dot product between rows of our original matrix. So we can actually get the entries of the Euclidean distance matrix from the inner product matrix, which looks close to our original matrix as well. In fact, we have found a pretty neat trick to compute the distance matrix from the inner product matrix as well. If you do have to find the entries, you just look at the row and column of what your entry is in, add the diagonal elements, and subtract twice the entry from them. In this case, it would be 8 plus 10 minus 4 times 2, which gives 10. A couple of other things you may have noticed about these matrices is in the distance matrix, you have zeros on the diagonals. This makes sense because an object's distance to itself is zero. This also makes sense in our new formula if you just plug in m equals L. Finally, an important thing to notice is that the inner product matrix is also symmetric, so that will be actually useful in our next steps. To summarize this investigation, we've basically found a nice intermediate for when we go from a matrix of points to a distance matrix. But remember, we're trying to find the reversal of this. Before we do though, there's a bit of a nuance we have to clear up first. I said nuance, but it's more of a nuisance actually. The thing is that when we went from our original matrix to the inner product matrix, we actually lost some orientation information. This is because the same set of points when rotated can form basically the same inner product matrix. Also, when going from inner product matrix to Euclidean distance matrix, we also lose position information. Luckily, in our context, a map will show the same information regardless of which way you look at it. As long as we preserve those distances, we should be fine. What we're going to have to do is standardize something here, so we end up working with the doubly centered inner product matrix. What this means is that when we're going the reverse way to find E to B, out of the many possibilities of A we can get, we're just going to find the one which places the centroid of the data at the origin. Let me introduce the centering matrix as well. You know how to calculate the mean of a set of points. Well, we can do that in linear algebra for a column vector by dotting it with a vector of 1s and dividing by n. Using this neat little trick, the centering matrix calculates the mean and takes it away from each column of A. Geometrically, we are sort of just shifting the x and y coordinates so that the centroid of the data is at the origin. By choosing our pseudo A to be centered at the origin, the condition we end up placing is that 1 is an eigenvector of our original matrix, with an eigenvalue of 0. It can also be proven that if 1 is an eigenvector of A, it will also be an eigenvector of B, with eigenvalue 0 again. It will also be an eigenvector of B transpose by the way we've constructed it. This is basically a fancy way of saying that the row and column sums of B will be 0. Knowing this, we can now go use our original formula to do some interesting manipulation to get the reversal going from E to B. First, from our formula, let's just rearrange so that the entries of B are on the other side. Next, we're trying to find substitutions for these two terms in terms of our distance matrix. Now, to find a different way to formulate those, we sum over the rows of the distance matrix. In terms of how we are summing on the inner product matrix, I made this visualization for the first row sum. The first entry will be the top diagonal plus the rows diagonal, which is just itself here, minus the entry itself times 2. The second diagonal, however, will be the top diagonal again, plus the row diagonal minus 2 times the entry. So notice how if we keep on summing, we're adding the top diagonal each time, hence the n next to the formula on it, and we're also adding the diagonal sum. And finally also subtracting twice the row sum. So our formula ends up being this. A similar column sum formula can also be found. But if we're trying to find the centered inner product matrix, those row sums equal 0. And so does the column sum. So we can simplify our formula now. And the final piece of the puzzle is the grand sum over the Euclidean distance matrix, which ends up being n times the diagonal sum times by 2. Now we can finally find a formula for the reversal going from E to B by rearranging the formulas a little and subbing them into our equation. After a bit of tidying, we end up with this formula, which can also have a neater way of interpreting in terms of averages. If you didn't follow any of that, don't worry, because there's a matrix version of it anyway, where we multiply it by the centering matrix twice, hence why it's called double centering. and it's pretty much equivalent to what we just did. To summarize so far, we now know that we have lost orientation information but are still able to find a possible configuration by retrieving the centered inner product matrix from our dataset using some matrix multiplication. We now have our centered inner product matrix, B prime, which is symmetric and looks kind of like the square of A. It would be pretty useful if we knew how to find the square root of a matrix. It turns out we can find the square root of a matrix, but we have to meet two conditions. It has to be symmetric and positive definite, meaning the eigenvalues will be positive. And both of these are true for our matrix, so we can find something known as the eigen decomposition. Eigen meaning special, decomposition meaning breakdown. Specifically, we're breaking it down into eigenvectors and eigenvalues. Most programming languages will probably allow you to find these, and I've used the singular value decomposition in this implementation, which basically decomposes our matrix into three matrices: the eigenvalues, which are placed diagonally in the sigma matrix, and eigenvectors are stacked as columns according to their corresponding eigenvalue in the U matrix. The V matrix in our case just ends up being U transposed, or the eigenvectors stacked in rows. This is a part you should use a computer to do, and because computers find these iteratively, you'll probably get some rounding errors, but that's fine for our use. So before we finally calculate the square root of our matrix, let's look at why these eigenvalues are so special. Here's a very useful plot of the eigenvalues in descending order. This is the key step to finding the dimensionality of our data. We plot the eigenvalues in order and basically see if there's a fall in them. The bigger the eigenvalue, the more useful the eigenvector is for when we project the data into that direction. Notice how in our case we have two positive eigenvalues. This is the dimensionality of our data, and if it were three-dimensional, there would probably be three positive eigenvalues. Also, we should be expecting a zero eigenvalue, and notice how after one zero eigenvalue, the rest of them are also zero. Now, we can finally find the square root of the matrix and plot. To find the square root of a matrix, just square root each of the eigenvalues and multiply by the corresponding eigenvector, and then just stack those vectors into a matrix which you can plot. Here is the result. I've plotted the original points in white and the new points in red. Everything looks a bit off, and when you draw the lines, yes, it is. But remember, we lost orientation information, and if we just rotate, we'll see it kind of lines back up. And it has completely preserved distances. If you thought that was satisfying, here's a quick montage of it on some other points.
So let me see you dancing, get that body bouncing. Don't stop till you're feeling like you're hiding at the mouth. So let me see you dancing, get that body bouncing. 'Cause I won't stop till you're dancing like a freak with someone else. So let me see you, yeah, I know that felt good, yeah. And you can't deny that a lockdown makes you wanna lose your mind, yeah. So enjoy this moment while you're feeling free, yeah. Let me be your showman, here's my slogan, dance with me. So treat it like that, keep it like that, beat on all those feelings like that. Pay for something, ain't no trusting, not until you show them that you're thinking like you're drinking. Let them see your worries shaking, everybody at the party waiting till you show them. And everybody knows it, can you feel the tension?
From that montage, there may be a few things you notice about the output of MDS. Firstly, sometimes you will have a reflection of the original points. So orientation is something that can be argued over, and you'll have to find other techniques to try and understand the orientation of your data. Next is something more subtle. You may have noticed that sometimes the points are laid out so that horizontally they are wider on the x-axis than the y-axis, and this isn't a coincidence. You can even see this on the Sierpinski triangle, in that it is orientated in a way such that it is stretched out most in the x direction. Why is this? Well, it's because when we have a larger eigenvalue, it actually corresponds to projecting our points in a direction with a larger variance. Allow me to explain. Here is a point cloud, and if you shine a light onto that cloud, we get a shadow. This shadow is basically the projection of the points, and in this case, it's in the x direction. What MDS will do is it will find the best orientation of these points such that the projection has the greatest variance. This projection gives us basically a window to look through into our dataset so that we see the most variation in the data. And thinking of higher dimensional datasets, projecting like this is useful as you can have, say, 5 windows that look into a 10-dimensional dataset and show the useful parts of that data. Alright, here is a concise summary to help implement this algorithm and interpret the results along with some code. We have 3 key matrices we want to understand how to go between: A, B, and E. A is a matrix containing our coordinates stacked in rows. B is just A multiplied by its transposed, and we call it the inner product matrix. E is the distance matrix measuring the distance between points. We're using B as an intermediate between A and E. We can go from A to E via B using this formula we derived in a double for loop. When we went from A to E, we lost orientation information, so we'll have to figure that out using other information depending on the context we have. To go from E to A, we use double centering on E to get B prime, which is the centered inner product matrix. Then we find the square root of B prime using the eigen decomposition. We just require the eigenvalues and eigenvectors. Plotting the eigenvalues, we're looking for a drop in them to see what eigenvectors we should project our data on. If the eigenvalue is greater than 0, then it can be somewhat useful. The greater the eigenvalue, the more variance the projection will show when projected in that direction. Then we can choose our dimensionality using the eigenvalue plot, and to finally plot, we find the square root of the eigenvalue and multiply it by the corresponding eigenvector. Then you can plot the principal coordinates and look for patterns. If I gave you that table of distances, this is what you would have to do to know what your room looks like. And also work out the orientation, but that should be pretty easy if you just know where 2 points are, like your door and table. But that's been classical MDS. And there's actually a rabbit hole that goes deeper than this, because mathematicians are trying to generalize this method to not just use Euclidean distances. I won't go too deep into the math here, but we'll start off with a gentler way we can make things non-Euclidean. One example I had given at the beginning of the video was a table of distances from town to town of France. So, if you imagine France had disappeared and the last piece of information you had on it was this table, then running MDS on it would give you this eigenvalue plot. And what you may notice on this plot is that there are negative eigenvalues. Now, we're still going to use 2 dimensions since there's a clear breakaway from the first 2 eigenvalues, and maybe we could even include a 3rd dimension if we wanted to, but why are we seeing negative eigenvalues? As it turns out, it's due to our dataset having some mismatches of distances. Realistically, the data was probably measured going from road to road, and sometimes there may be one-way roads or roads that twist and turn a lot. So this would be different from the Euclidean distance, because a journey forward may be shorter than the return journey, or vice versa. This would make our distance matrix not symmetric, and hence our inner product matrix not symmetric, which is why we get negative eigenvalues. Still though, when we plot the map, it's not too bad. You have to remember, this is a different type of world, which is non-Euclidean. Either way, this would probably be better than not knowing what France looks like at all, and in contexts where you're not sure of the structure of the thing you're trying to find, such as archaeology, this is actually very useful. And in fact, we can start to make more new worlds with new types of metrics, which are really useful for real-world datasets. If you're programming this using a package, you may notice that the distance function can have a different argument. What this function will do instead of calculating the Euclidean distance is calculate a different metric instead. Then it does some extra calculations and basically approximates a distance matrix that we can do a similar technique on. But being able to use different metrics is extremely useful for real-world datasets. And there are also methods that even exist to be used on dissimilarities as well. Think, for example, how you could describe the dissimilarity between people. It kind of depends on the information you have. So let's say I gave you a dataset of the top 1,000 users on Instagram. Using that data, what kind of map can we make? Well, let's first attempt to use the classic technique here, and then I'll talk a bit about metrics and their definition. So, following the usual technique, here's the eigenvalue plot, which suggests a dimensionality of 3. I'm just going to plot 2 of the dimensions, but do remember 3D plots are still possible. I started with a plot of just 32 users, and then 100, and then finally 1,000. The patterns I think are forming based off of my own intuition and knowledge of social media aren't too concrete, but I think it looks like a flock of birds flying towards something or away from something, which suggests competition, right? I mean, that probably makes sense because we have specifically picked the top 1,000 users, so there is going to be some sort of competition involved here. Aside from that, we can really just see a big cluster on the top right, and the clustering seems to be very intense there. We can sort of see some artists like Selena Gomez, Beyonce, and Kim Kardashian being together, which must have a similar audience, I guess. But it doesn't really stand out to me very well. So instead, what we'll do is plug in a different metric. But before that, let's just define a metric. Metrics are basically how mathematicians have generalized what distance is. They've basically found the essence of a distance. If you have a function d that takes in 2 points, as long as that function follows these 3 properties, it is a metric. And in whatever world you're in, it is basically a form of distance. The first property is that distance should be positive or 0, because we don't really want any negative distances. Second is that the distance from x to y should be the same as y to x, basically meaning no one-way roads. And the third property is the triangle inequality, which basically means taking a path from x to y by going through another point called z should take longer than or be equal to going straight from x to y. This means that we can basically tailor our metric specifically for our dataset, provided it meets these properties. I'm going to use the Canberra metric because it's normalized and was available in the package. As you can see, the result is quite interesting, and I think it kind of looks like a donut with a bite taken out of it. Looking closer at the bite, I noticed that on one side we have music artists like Justin Bieber, who cater towards a female audience. And on the other side, I noticed The Rock, who probably has a male audience. So I think that this bite could probably be a sign that there's a gap between gender roles. So if you're looking to start an Instagram, you may want to cater to a male or female audience. Or maybe you could see this bite as a new niche to fill. Of course, I could be wrong, and we'd probably want to investigate with more data, but you can see how the metric is useful for finding new patterns. So, I hope you can see how multidimensional scaling can be really overpowered for scaling down the dimensionality of your data. And it has a lot of really good applications like in biology, social science, and archaeology. Remember, you can make a map on basically any dataset by tailoring your metric to it. And there are even variants of multidimensional scaling that can work with missing values or really unclean data. But hopefully you understand the idea and see how it is useful. One really useful application is in recommendation systems. And since this video isn't on YouTube, do like and share this video if you think it'll be helpful for others by showing up in their feed. Also, please do consider subscribing, but only if you don't mind math memes in your recommended feed, because I tried to make this video more timeless. Aside from that, I think you are now armed with the knowledge required to go into the real world and analyze your own dataset. So do go to Kaggle and attempt to use this technique, and maybe even make a post of it if you find something really nice. I'll also link some extra resources in the description if you want to use them.